Okay, hi, remote student, can you hear me?
Yes.
Okay, great, thank you. Okay, so I'm going to talk about two things today. First, I just want to very quickly show you what the reference implementation looks like. So it will help you, and in the process, I actually simplify a little bit from the, you will see why. I simplify a little bit. Let me actually go here, okay. By the way, I haven't uploaded to the GitHub yet. So right now I'm just showing you the code looks like. I mean, the most important thing about this is try to implement the interaction between this 5 program. So if you take a look at the makefile, it essentially has 5 program as indicated in the homework assignment specification. Let me get rid of this so I can have more space that you can see. Okay, so there are 5 executable files. One is mini GFS client. One is master. One is primary representing primary replica, and secondary A and secondary B. Okay, and it's just 5 program is being created here. And what I make the simplification is that in the GFS, if you remember, when the data chunk, let me just bring the GFS paper again. I hope Google is smart enough to give me this answer immediately. Okay, we're not looking at this picture. We're looking at this picture, figure 2, right? We have a client, master, primary, secondary A, secondary B. So the simplification we do here is in this picture, remember, the data chunk was actually pushed this direction. So it's actually go to replica A, and then go to primary replica, and then go to secondary replica B. At least the figure shows that way. And when you try to commit the change, the 4 to 7, you actually go through the primary replica. You go this route and have primary replica contact both secondary A and secondary B, right? That's the paper. Okay, to be honest with you, unless I see the code they implement, I'm not confirmed they're doing exactly like this. But the intention is clear. Intention is try to make sure that you will not go through the same network paths to do both of this. So you can get some advantage such as load balancing or network performance. Okay. So for the for the simplification I want you to do is that we're not going through this route for data. For data, when you want to push so what's happening is when I want to write something to the data, this is basically, in case you're not familiar with it, this is a write. This is not read. I want to write something to this 3 replica. So the idea of GF is a read. When you do read, you can read any of the replica, is fine. But when you write, you have to write to just 1. Okay. So essentially, what you do is that the simplification is that when you want to write 3 replica, you don't need to go through client to secondary replica A, second B, and such as that. You just directly client to secondary A, client to primary replica, client to secondary replica B. Functionally, they're exactly the same. It's just they go through a different route. But the implementation will be a lot simpler if you go that route, okay? Meaning that you don't have to kind of forward, and decide who's next. That simplifies a lot. So basically, it's a client to directly to this 3 replica for message 3. in the same token, when you want to do this 4 to 7, means you want to commit or abort. So from 4 to 7, what you want to ask the replica to do is move the file from the private to the public. Your private copy, and then you move to the chunk. So essentially, also, you don't actually need to say, let the primary replica to take the lead, and let primary replica to contact the other one. So the simplified implementation is just client directly. This client is acting as a role of the primary. So essentially, this is a very standard two-phase commit. So the client is directly contact all three of them again. So essentially, I'm actually removing this kind of, trying to do this kind of optimization to do the pass. Instead, it will be simplify the design if actually client will actually handle this part of the okay. So that has some complication, like for example, how do you actually handle the sequence number, but we'll handle that a bit later. Don't worry about that. So, okay. So therefore, the most important thing in this implementation, by the way, this is actually directly modified from mini NFS. So this is my habit. This should be your habit, is try to implement the simplest way is to try to find something which is close and then try to modify. That's usually the best way to do. So if I'm going to use, if you remember that this is the mini NFS, that JSON's gone. Okay, mini GFS. So this is essentially the remote procedure call. The JSON RPC, I define a few functions about how the 5 programs they should communicate with each other. So the first function is called obtain chunk URL. It's obtain chunk URL. So the chunk URL is going to be called from the client to the master. So this function is actually only used between the client and the master. So when you want to obtain the chunk URL, in fact, I should put an S because there are 3 URL you need to find for each of the replica. So essentially what you get is that you have the action, which is whatever function you would like to do. And then of course you want to search for like what file I want to get the URL. And you can say, well, what is the F handle to that URL, to that file I want to get. And then you have to provide the chunk index. Of course, in this program, I said the chunk index is going to be only 1 chunk, right? So to simplify a lot, only 1 chunk. But I still want to have a placeholder for me to later extend it to have multiple chunk index. So this 3 is being sent to the master. And together with the standard 4 piece of information on the VSID, so you know that which later you will see is a directory object is going to handle this. And then you're going to return the chunk URL. So basically, it's a 3 URL being encoded as a JSON. So everything we're passing is JSON strings. It's so easy for us to actually handle this. So this is going to be a obtain the chunk URL. Okay, so that's the one function that's actually communicate between the coordinator and the master. And the second function is try to push the file to the replica. You see, right now I have only one function. I call it push chunk to replica. So essentially, I'm going to call this function 3 times. Each time to one of the URL, because the first function gave me 3 URL. The second function, I'm actually going to call push chunks to URL. That's actually corresponding to message number 3 in this picture. I'm actually going to push the data down there. So if you look at the parameter, is again, action, file name, F handle, chunk index, those kind of things is just provided there. Your program might not use it. An argument The important is the argument. The argument here is going to be encode the data itself. So it's going to be encoded as a string, but there is an encoding that's actually you can convert a binary file into a string. And that kind of conversion, because JSON, one of the limitations about JSON is that JSON can handle the basic data type, string, number, whatever. But one thing JSON cannot handle is binary data. So therefore, we use this kind of conversion to convert a binary data into a chunk of, convert the chunk into a string. And what's the negative consequence about doing this is that your data will be about 30% or 20% more because of the encoding. So if you want to have a chunk with 64 megabytes, I mean, in this program, please don't try to do this kind of big chunk. Try to make you can control the chunk size. So make the chunk size a little bit small. So assuming your chunk size is about, say, 256 bytes, then the encoding of that into a string will become something like 300 bytes, because you have to consider all the binary situation, and then you just use the same function to convert it back. I will provide you the function to do this conversion. Okay, it's pretty standard. For anybody want to use JSON in the web programming, they all have to deal with this problem. It's unavoidable. I mean, unless you want to be really efficient, when you want to send a big chunk of data, I believe GFS, they are not using this encoding to just save bandwidth. But then you need to worry about how you're going to send that part of the data differently. I mean, Google developed other kind of standard, but I feel the difference is that with JSON, is actually the concept is the same. And wasting some memory, but it's much more human readable. We use Google's, they have another format, I forgot what they call. It's good, it's working exactly like JSON RPC. I think it's called gRPC or something like that. But the data format is not humanly readable. Otherwise, they're the same. Okay, so that's actually basically push the chunk to replica. And then the result is the status. So you're going to get the result back saying that, hey, I pushed to you. I mean, are you going to coming back to me saying that, oh, this fail or it's a success, right? It's either fail or success. Fail means that either I actually don't think I'm actually managed for that chunk, or actually the server is just essentially not online or something, okay? So that's a status for the second function called push chunk to replica. And the third function is just representing 4 to 7 message is commit or abort. Because the second message push the data over there, if you actually get all 3 success, that means your chunk has been successfully placed in each of the replica. And then you just send commit or abort again to those 3 URL. So you actually use the first function, obtain chunk URL from master. You have 3 URL, then you're going to use that 3 URL to contact 3 different servers. All right. And then commit abort is actually fairly simple. It's just basically everything is the same, like we've seen before. And the only argument is basically tell each of the replica whether they should just move that private data to the public area, or they should just ignore, just erase the private data. Okay, it's really just 3 functions. And you essentially can do the whole mini GFS operation for the homework assignment number. Okay, so I just give you a little bit example. So for example, directory.h, which is the way I implement. When I implement, I think what is master? Master is actually handling the directory information, where that is. So I'm actually, naturally, I'm using directory to actually handle as the master. The chunk server, they know nothing about the directory structure. All the directory structure is included in the master. So you can see that what I did is directory entry, that's for each of the file. That's actually what I care. So over here, I basically have the name, have the F handle, chunk index, and then chunk URL. Basically, I keep the chunk URL contained over here. And what happened is when you actually call the function, you actually call the function here, obtain. The way I actually implement is obtain chunk URL. I actually put it in the directory because directory contains everything. So when I receive this chunk URL, I'm actually look at the three information. The three information is a file name, file handle, and chunk index. I use the three information to decide which directory entry that's actually hosting that particular chunk. And then I just basically go to the directory entry to retrieve the URL information and encode it as a JSON and then send it back to whoever call it. Of course, okay, by the way, you can do this without using RPC. The first implementation you might want to implement is that everything is actually local, right? It's just local. See, the thing is that it's going to be RPC when I have a shadow directory or shadow chunk. But you can actually try to see your program will work with just directory.h and then the chunk.h. So everything is local. To simplify that, and then you essentially sequentially send the request to this three object, the primary server object, to be able to handle that. But once you actually see that, okay, my directory, my chunk looks good, then you basically split the logic, start to use a shadow business to actually have those 5 programs working together. Okay, so that's usually just a software development habit. You might have a different way to develop. It's just for me, I always try to simplify the problem to the level I cannot simplify anymore. And then I make sure that work. Then I start to make it more distributed. Okay, but the architecture, the logic is, for example, I don't want to include all this extra function. I just want to have the 3 function. I feel the 3 function is sufficient enough for me to be able to handle the whole workflow about the file. Okay, any question from in the room or from remote? Okay, you will have more questions when I release to GitHub. Okay, don't worry, and we can discuss. I mean, I mentioned this at the end of the last class. I mean, this is not for you to feel a lot of work, a lot of pressure and try to do programming. It's just for you to experience how you can actually do a little bit to actually be able to grasp the concept behind a very complicated system that we're using. That's really the power of computer programming, in my opinion. Software engineering, particularly, it really the system looks complicated, but if you can actually start programming, understand, then essentially your concept, your understanding about that system will grow as you start to make the program more complicated, including more feature. Okay. All right. So. Okay, I'm actually going to continue a little bit about what I talked about last week, not last week, Tuesday, and then go into apply the social informatics to a general distributed system architecture. Okay, so this is what we talk about. It's an email, and we try to use the email to be able to support a particular application from the beginning to the end. How do we actually connect to that? And I didn't actually show you. I actually show you this picture. And by the way, this is just, if you heard about Genie, which is global network, global environment for network innovation, which is a big NSF project. So DSL was one of the first few projects that's actually get implemented on Genie. So what I didn't show you is this slide. I was trying to, where's my slide of my Thunderbird? This is actually your email client will look like when you actually look at the email. So we actually add a few things. We add a few plugins to the email client. So the one plugin is, you can see that we have called DSL Trust. So we actually compute the path that's actually going to deliver this email to a particular person between the sender and receiver. So essentially, you will be able to start to, by the way, we have two different ways of calculating the score. It's an algorithm. How do you actually believe that this particular path is actually trustworthy or not? So we have two different ways of compute. So that's why you see two different columns you can actually compare. So our way of thinking is that when you actually try to try to sort through all the email you receive, that if you actually see that you have a good pass, then you can actually sort it out and such that you won't miss those emails that's truly important to you. Okay, that's one message. But on the other hand, I'm actually going to challenge this view as well. I always like to critical thinking about anybody's work, including myself, is that will this have some kind of negative impact? I mean, if I'm actually using the system, then all the things I'm receiving is essentially an echo of chambers. I don't know if you know that, it's called filter bubble. So that number over here is a filter bubble, because why? If there is somebody from another country that really want to contact me, well, there is no way, because he never have a pass that's out to show any decent number, right? And then how do I actually connect to that? I will actually talk about that today in architecture. So essentially, any technology has its purpose. This technology does not help for somebody I don't know, but I should communicate with to contact with me. But this technology will help you. If you do have some connection, you won't miss it. So that's the purpose. So you can see that when you click one, it actually shows the Facebook picture of the user on the down below. For example, this is actually, by the way, this is actually my wife's account. And it's me and one of my students. So when I did demo, guess what? I used my wife's email account to do that. So that's very interesting. I mean, it's kind of funny when we actually do that development. Okay, so that's what we did. And the other thing which I forgot to show you the picture is actually the program to do this kind of conversion. That ideally what we want is that instead of letting application directly connect to Facebook, we want to be the gateway or the network address translation or firewall that in between all this application and the Facebook itself on behalf of the user. So the user can actually customize this part to actually say, well, what kind of transformation I would like to apply to my own social informatics, and such that I can actually get the best out of the system. So having said that, I mean, some of you, probably none of you know actually in this room, that I actually spent a lot of time working on what I call misinformation, fake news, especially in the past few years before the election. And we look at the left wing and right wing and different kind of media, how social algorithm is distribute this information to all of us. And you clearly see that your political inclination is actually being reflected really well in the social algorithm, the Facebook, and to a point which you kind of feel bad because you lost that diversity, you lost that other thing which is important. So that's the thing we always worry about. The modern technology, the data-driven technology like machine learning or any kind of AI social algorithm, is trying to determine for us about what we should talk, what we should eat, and what we should read. And that's kind of reinforce our view on certain things. I mean, usually people use the word filter bubble or echo chamber. But the issue is not just about what you're receiving about your echo chamber's response, but more importantly is that you lost the control about what kind of things need to get back to you. So the thing is that what we really want to define the transformation here is that we want this person. You're the one who actually own all the social informatics that Facebook or Google collected for you. And we really want you to have some control to say, hey, I really want to do a transformation about your view about me. And then let's see what I will get. Okay, so that's actually the architecture. So that's why we actually be able to do a little bit at that time that you have the window to actually say, you can see that I'm actually creating a virtual social network. So there is a virtual social network that actually has a path that's multiple hop. And what we can do is that we can actually be able to say, hey, I actually not the direct friend of this person, but I'm a friend of that person, 3 hop from me. But I really want you to treat that he's my direct friend when you actually talk about influence, because that particular person really have a great influence on me. So that's the idea of whether you can do this blocking and that. And I think this idea until today is still lacking. We don't have that control. We basically let the whatever social media company to control the whole thing. Okay, so now I'm actually going to apply this to a general context. The general context means it's a distributed system. So the first target, when I look at the distributed system, I'm looking at the largest distributed system that human ever created. Is called internet. If you think about internet is a distributed system. It has an infrastructure to allow us to communicate with each other. Okay, I have a question. I'm not going to go into any kind of networking detail. Any of you have heard about a protocol called BGP, Border Gateway Protocol? Okay, some of you, probably two of the students heard about this term. So essentially, internet, if you want the internet architecture, you really should understand 2 protocols, in my opinion. Those protocols are designed for a long time and we're still using it. If either one of the protocols die, then essentially the whole internet died. So the first protocol is DNS, domain service. I mean, DNS is so important to a point when FBI want to shut down a service. Want to shut down, there is a service is harming either our country or harming our business. What do you do to basically the easiest way to take care of that is basically remove that from DNS. So the thing is that when people want to access that service, it's no longer can transform to what? To IP address. DNS is basically, they can do a lot of this kind of record transformation, but the most common one, among other things, is actually transform name to IP address. To IP address, so you can convert that. So okay, that's DNS. I'm not going to talk about DNS today. I'm going to talk a little bit about BGP. So what is BGP? BGP is allow every single node that's actually connected to what we call the internet will be able to talk to each other. So essentially what BGP is doing is try to allow every system, more specifically, we call it autonomous system. The autonomous system is going to announce what range of IP address, or sometimes we call IP address prefix, that we can actually announce. So for example, UC Davis, I can announce what's UC Davis IP address. Anybody can remember that? What's UC Davis IP address? Okay, 169.237. something. Okay, if you see any IP address was 169.237. something, that's UC Davis address. So essentially, UC Davis, what we call autonomous system, UC Davis is an autonomous system. I'm not going to more complicate. There is another concept called multi-homing to improve, but let's just simplify. Say UC Davis announced 169.237/16. Let's just say that is called IP address prefix, meaning that anybody want to talk to UC Davis through this announcement from UC Davis as an autonomous system to many other autonomous systems, they actually will be able to find a path to actually reach us. So essentially, what BGP is doing is that we have a bunch of autonomous systems in the whole world. And some of these autonomous systems, they connect directly to each other. For example, UC Davis directly connects to California Education Network, which is also an autonomous system. Or we connect to AT&T, which is multiple autonomous systems. And so essentially, we connect to each other, and we tell each other what IP address prefix we know. And gradually, when this propagates to everywhere, then anybody in the whole internet can actually find a route to reach anybody in UC Davis. That's the concept of global connectivity. Yes?
Is BGP, isn't that why like Facebook was down a couple months ago? Like, like a couple months ago when like all the Facebook products were down for like a day, was that related to
I didn't look at that. I didn't know that, but many years ago there was an attack in Pakistan. Oh, no, not Pakistan. There was an attack on YouTube. So let me actually tell you, this is 2000, I think it's 2008, because YouTube has a content which is unfriendly to their culture in Pakistan. So people in Pakistan asked YouTube to remove. So what, YouTube said, no, I'm not going to do that, okay? Understandably, people have their opinion one way or the other. And what happened is that at that time, Pakistan Telecom, which is AS, they announced YouTube's IP address. So in that way, you actually have two what we call original AS. One is the real Google one, and one is the one created by Pakistan. So what happened is half of the world, their traffic is going to route to Pakistan. Half the world is routed to Google, depending on your routing decision. But that was interesting. That's why BGP, they trust all the autonomous systems to do the right thing. And with that case, of course, there is a way we can handle that. That's going to be another 3-hour lecture. I need to do for 252 only. But that goes back to the question. It's very easy for any company, their network is down because something unstable on BGP. People work hard to make sure BGP is stable, but still they have glitches. Yeah. Okay. So the question I want to ask you is that what's the purpose of BGP? The purpose of BGP is actually allow every single IP address, as long as you hook to the wall or hook to the Wi-Fi, you will be able to connect to every single IP address in the world. Okay, so I'm going to ask you some questions. Do you want to guess how many autonomous systems the world has right now? I'm saying UC Davis is one, AT&T has a few, because AT&T is global, so they need to have a few, okay? How many do you think we have autonomous systems? Anybody want to guess? A lot, yeah, a lot. And it's growing, by the way. Yeah, okay, we can actually take a look at that. The number I show here, I said 30,000. This is many years ago when I first gave this talk. And the second number is called prefix. I said UC Davis are now 169.237/16 or something, IP address block. We announced to our neighbor ASs, and our neighbor AS will continue to propagate to the whole, essentially all that IP address prefix need to be announced to every single autonomous system, right? Otherwise, we cannot connect together, right? So that's the internet architecture. So let me just show you what is today. I mean, before I came to this classroom, I actually just check. Here's a website. You can check anytime about the status. Okay, so let's look at, this is called CIDR report. So the CIDR report, this website is continuously tracking how many autonomous systems we have, how many IP address blocks. So if you go down a little bit, it basically say at the time, right now, today, we have about a little bit less than 900,000 prefix IP address prefix. The one I showed you was a few years ago was 300,000, right? So we actually already tripled the amount of the IP address prefix. I believe all those are IPv4. It's not even v6. And then autonomous system today has 73,000. This is about double. So there are more autonomous systems that join the whole internet. And this number just keeps growing. Let me actually show you how it grows. If you look at the BGP table, this is actually number of the route entry. Right now, you see it's about 900,000, right? But this is how it grows. In the 1989, it's almost nothing. You cannot see it. And then it's actually keep growing like this. So remember I showed you, what was the number I have on my slide? It's about 30,000. So 30,000 is when I can see how, it must be somewhere here, right? It must be 10 years ago. In about 2011, 2010, when I gave this talk, it's about 300 prefix, but now it's about 900 prefix. Okay, the system is actually keep growing, and the system, in fact, has some concern about scalability, which is the 99% of computer science work is dealing with scalability in distributed system. Okay, and similarly, just want to show you this part. It's an autonomous system. It grows this way as well. This is the AS, unique autonomous system. It started with very small number of autonomous systems before 97. And now we have more than 70,000, more than 70,000. So the number I show you is also about 30,000. That's about, around here. It's about 2009, 2010, about 10, 12 years ago. Okay, so that's kind of just give you an impression about the size of the internet we're talking about. So essentially what BGP is doing is actually make sure that every autonomous system, every autonomous system will know the routing information to every single prefix. So any of this 90,000, well, how many do I have? No, sorry, 70, let me quote the number. Today, any of this 73,000 autonomous system, they need to have a routing information to all of those 900,000 plus IP address prefix. That's the scale of the information you need to do. If you don't have that, our internet is not connected. Is there anything glitch, like you mentioned, Facebook or Google has any of the issue, they have a glitch, then things will falling apart for a short period of time. Okay, so this is just tell you about how we try to provide called global connectivity. Okay, why I'm talking about this? Because I have a problem with this architecture. Okay, So the architecture allow, oh, sorry. The architecture, in fact, allow anybody to talk to anybody. Because if you can get one of the IP address from those 900,000 prefixes, then you will be able to connect with any of the IP address. So that's basically global connectivity. So before I actually show you my biased opinion, because I have a huge debate with lots of big networking guys always on this topic. Do you think it's a good thing or bad thing to have a global connectivity? Yeah, sometimes good, sometimes bad, right? I mean, the global connectivity is very convenient for us to connect to everybody. But that also means anybody can actually contact us with any kind of malicious information. So it's always pro and cons, right? In terms of global connectivity. And in fact, there is one major question I always ask myself, that why this particular attack will happen in today's world. Because we also wonder, I mean, when we're doing cybersecurity, some of you might know I'm a cybersecurity researcher. We always think about, oh, how do I define this is an attack? How do I actually remove this attack, right? That's pretty much what we care. But the thing is that I have been actually asked this question. I said, what fundamentally is the internet architecture enable the attack to be possible in the first place? So if you look at the few major attack that in the internet history, the first one very noticeable is worm, internet worm, or sometimes called botnet. They actually penetrate the network and propagate an internet worm. And then there is, of course, spam related, spam, phishing. Those are basically, I try to send information to certain targeted, okay. And then there is called denial of service attack, Ddos. Have you heard about Ddos? It's essentially I compromise lots of machines in this architecture, ask them to saturate the network at some time, either knock down Facebook or knock down Google. Okay, so that's actually denial of service attack. So essentially, I'm actually starting to question myself is that this architecture promote global connectivity, but it actually promote a very important element that without this element, the attacker will miss a lot of opportunity to do a lot of things. Okay, so I actually pull back the argument people usually, I mean, by the way, this is open forum, so you can actually share your opinion, because I sometimes feel I shouldn't be too strong on stand. But usually my argument is that if we provide global connectivity, we want everybody to connect with everybody. And yet, the people that doesn't have a social connection with me, the chance he can connect with me is very slim. So it means that in layer 3, or even in email protocol, you can actually deliver a piece of information from one email account to the other, or you can deliver a packet from one email address to the other, because that's this architecture allows us to do. But whether that email really effectively come to my attention is actually not guaranteed. So essentially, we provide a global connectivity of a technology in a distributed system. And to me, that's not enough. And not only that's not enough, but it could enable a lot of attacks to happen. So now I'm actually thinking, do I want that capability or not? So I'm actually going to present a different architecture that's actually thinking about distributed system without what I call global, unique, routable identity. So let me actually tell you, what do I mean by unique routable identity. So your email address is a unique routable identity because once I have your email address, I will be able to send information to your inbox. So, okay, I should actually say the other one is that global unique routable identity means that that identity itself is the only thing I need to contact you. If I know your IP address, how do I find out your IP address? Okay, you run the server on YouTube. And I realized that, wait a minute, YouTube, I use DNS. Remember, I have DNS. So I use DNS lookup, and I found out your IP address. I know your IP address, then I can launch Ddos. I can launch whatever against you. So essentially, if the routable identity is the only information I need to reach you, then we're in trouble. And that's what today's internet is providing. DNS, BGP together, that I will be able to do a lot of bad things against anybody in the whole world. Okay, so one of the idea, I want to actually very to the point. One of the idea is I should separate the routable identity and the identity itself. So one is a routing. Routing means that which AS I need to go through to talk to you. But the other one is really your identity. Because this two has to be the same. Can I actually design the system somewhat differently? Okay, so I'm actually going to challenge this. So this is the form of any kind of identity, including email address, including IP address, including URL. And if a URL is the only information I know to communicate with you, that's become routable identity. Okay, so how do I do that? I'm actually insert another layer, social layer, just the way I insert the email social contact. I actually insert a social layer into the communication. So what we're actually saying is that, okay, great. You want to communicate between point A and point B. And what I'm saying is that, well, you don't need to get the IP address, or you don't need to get a unique routable global identity. And what you really need to do is that, okay, I want to see where me and the person I want to communicate, where are we in this green layer in the middle? Because communication is always about relationship. How two people, they can relate to each other, so I can manage that. I will go back to the issue that how do I actually address people that I don't know. For example, somebody, this morning I was teaching the ethics class. I was actually showing them how Nigeria is a country that actually has a serious poverty problem, but again, they have a bad name in terms of receiving, for example, such as a spam. And how does somebody from Nigeria be able to communicate with anybody at UC Davis when we default that's actually Nigeria email or context is usually spam or scam? How do they actually connect with us? That's an issue I'm going to hopefully address at the end of this lecture. But I want to actually tell you what is this architecture. So this architecture essentially saying that, okay, I'm actually, if I'm going to connect with somebody else, I'm not going to rely on what I call global routable identity. I'm actually going to rely on an online protocol that allow me to find out my relationship with that person. And if that relationship is actually solid, and then basically that relationship will provide me a route for this two person to actually communicate. So instead of having an infrastructure guarantee every IP address will communicate to IP address, what I just provide is there is a network of social resources. And when you connect to a point, the system will discover that relationship. If that relationship being discovered, and that relationship will be pushed down to the network layer to find a path to actually for you to communicate. So that's actually the whole idea about social control routing. Okay, so I already showed you this email idea. And let me actually use this to describe. No, I'm going to skip this part directly to, wait a minute. Okay, sorry. I'm actually going to talk about this. So essentially what the architecture I would like to talk about is that you have two application entity. They want to communicate with each other. This could be an email program. And the thing is that this application entity need to has a one-to-one mapping to the social layer, which will including your social identity. So you can imagine this is like a Facebook. You have a Facebook, but the thing is that I don't want a single company like Facebook to actually control that. So the architecture we're thinking is more like decentralized. So it's a decentralized version of a social network in the middle. You can think about that way. But the information is actually communicating. It's like a Facebook relationship. Just think about that way. Okay, and the thing is that over there, before this two network entity, they can actually communicate. They actually need to run the protocol in the middle layer, try to find the appropriate social relationship. If they can't find a social relationship that's actually acceptable with some trust value, then essentially this two network entity will be providing a route for them to actually be able to communicate. Okay, you can see that I'm kind of simplified, but the middle point they need to actually provide as a part of the network entity as well. Okay, so that's the basic idea. But you asked the question is now I'm actually deviate from the DNS. So what's DNS? DNS is basically saying that, hey, I have a URL or I have a name. You gave me the IP address, I will be able to communicate. And I said, I don't have that anymore because I don't want anybody to have a unique identity, including your domain name as well. So I actually also abandoned the concept of DNS. And I don't have a unique IP address directly mapped to me at any time. So, well, how do I actually be able to find the other person? Because we don't have a unique name anymore. Okay. Yeah.
Does it Tor network already do this?
What network?
Tor, the onion router.
Yeah, I know. Tor, right?
So it also has like multiple layers so that the identity of the original person is concealed.
The design of the Tor, in fact, is a little bit different in the following sense. When you do a Tor, you actually need to discover what is the route you're going through to actually connect to that, so you know who's your next hop. So you actually provide an idea called onion routing. You might have heard about onion routing. So I have to already encrypt in a different layer, and I already know the route. I will actually go over there. So in general, when you use the Tor network, you're not looking at your social information, but you're looking at what is the Tor network, what is the node topology for you to go there. So I don't know whether Tor has actually changed, but in my concept, that Tor is still, everything is a layer 3 concept. So it means that they try to provide a routing. They just use the intermediate, like a bot as a infrastructure node for them to pass.
So
Yeah.
it's like complete anonymity. You're saying if at all the person is, if there is a social context between two users, we are giving a directory. If at all there is no social context, we are routing it to multiple.
Okay, I actually didn't have a chance to talk about the network layer. It might not have a direct link. So it could be it could be, for example, one of the scenario, maybe I want to do parental control. So there are some of the content. This could be working is that my one of the junior person want to go to a certain website which is not designed for junior, and it could be the parents actually in the middle. So the social layer will include the parents or guardian in that process, or even the doctor, for example. Therefore, the network need not be end-to-end. You need to first go to the guardian to actually check the content. I mean, check the content not for censorship reason, but for the reason of try to according to the policy. Yeah. I haven't actually talked about the network layer to push down. There's a different idea to do that. But I want to actually at the social layer to see, without global identity, how do I even be able to find the person that I want to communicate with? So that's an issue. I mean, think about this. Okay, you're asking questions. So I want to hit on this. If you want to communicate with me, for example, you have to know my email address, right? Otherwise, you cannot communicate with me. But if you have my email address, would I be able to handle your email? Probably not, because if I don't know you, if I have too many email, I just cannot, right? So what we want to do is that I don't even have your email address. We don't have any kind of routable identity, and such that I actually only looking at the relationship, can I actually construct a relationship path to get your attention? Because ultimately, we, as a human being, we care about relationship. So we want to know what relationship that this communication is coming in, and we will be able to establish that. Okay, that's the concept. But hopefully I give you some example, you will be clear about what we're trying to do. Okay, so let me actually try to say is that, well, assuming A wants to talk to D. Okay, I have a topology that A wants to actually communicate with D. And the network topology I show here is just social topology. This is not network topology, it's social network topology. So A wants to talk to D. The trouble is I don't even know who's D. Remember, I don't have any routable identity. I don't have any routable identity, so I don't even know who is D. But I want to talk to D. I have some information that I know, and maybe D will know that we like to communicate with each other. But the thing is that there is no such thing called routable identity that we can communicate with. Okay, how do I actually make sure they will be able to communicate? Okay, let's actually make things a different context. Let's say I want to actually find a McDonald's. I want to communicate with a McDonald's. Instead of finding a person, if I can find a restaurant, I think I can find a person. By the way, they're the same principle. I want to find a McDonald's. And the thing is that how do I actually find a McDonald's? You can basically using, say, the idea that we provide here is one of the ideas called keyword propagation. So if actually D is indeed a McDonald's, by the way, D might not be a McDonald's, might be just impersonate a McDonald's. And so potentially D can actually propagate to C, saying that, hey, I'm a McDonald's, a little bit like a BGP. And C will actually connect to B saying that, hey, I have a McDonald's on the other side of my node. And then B actually propagate over here to A, say, hey, I have a McDonald's this way to you. And now you can see that you have a lots of keywords or pattern being actually propagated at you. So you actually see a lot of keyword, and then you say, okay, I'm interested in McDonald's. And then I actually see, oh, here's a McDonald's from B. Okay, I'm going to do reverse routing. Just go to B, say, hey, forward this request to whatever McDonald's that you receive, and then they will actually reverse the path, and they can actually connect to that McDonald's. Okay, so that of course that's very expensive, right? You think about that, you have to propagate all kinds of keywords. This is almost like a search engine that Google tried to do, but I tried to do it in a decentralized way. Instead of having one company which is collecting all the keyword, linking all the URL together and give it to me, and then I'm actually going to do that in a decentralized way. Okay, so I'm actually going to do this using this way. This is the way we think about. is that, well, you actually need some way to help the focus and such that your keywords will be able to restrict it to a small number of keywords that's actually going to help you to narrow down. So of course,